Let us now move on to the next problem, problem number 28. And this problem is from crystallography. It says, consider the crystal structure shown in figure where black and gray spheres represent atoms of two different elements and A denotes the lattice constant. Let me draw the lattice for you here. So instead of black and gray spheres, I'm just going to draw two kinds of spheres. One is shaded and the other one is unshaded. This is a shaded sphere, this is an unshaded sphere, and they're placed alternately. So this is how it goes. Shaded sphere followed by unshaded sphere followed by another shaded sphere, and it goes on in every direction. This is how it goes on in all the three directions. I'll just draw one of them for you, and it should be easy to visualize how to basically go on in the other direction. And just like I said, the rule is simple: shaded followed by unshaded, unshaded followed by shaded. And this then we have the same thing coming down here, same thing coming down here, shaded, unshaded. Now you see, it looks very crude, but this is what the structure looks like, and the lattice constant is given to be A, and these two different shaded spheres denote two kinds of elements, and we have to find out, we have to basically see what is the Bravais lattice of this configuration, of this structure. And recall that there, look very closely. If you look at one face, you see how many atoms are there. There's 1, 2, 3, 4, 5, 6, 7, 9. And one of them is placed at the center, 4 on the edges, and 4 on the corners. You know that every atom on the corner is shared by 8 other cells. Corner shared by 8. The corner contribution is 1 over 8. The surface contribution is about half, and the edge contribution is about 1/4. And if it lies in the center, then it's exactly 1. And if you recall your solid state physics elementary course, there is a structure which looks exactly like this, and that is the structure of Na and Cl. You can consider these to be the Na atoms and these to be the Cl atoms, and you see basically that each lattice has exactly 4 Na atoms and 4 Cl atoms. And the structure of Na Cl is phase-centered cubic, FCC. So in this case, the most probable Bravais lattice is FCC as well, face-centered cubic, and that is our option B. So this concludes our problem 28. The Bravais lattice of this kind of configuration is FCC. Let us now move on to problem number 29. Problem number 29 is on solid state physics as well, but this time from transistors. So it asks us to consider a transistor. NPN transistor. This is an NPN transistor. If you recall, this is the base. This is the this is not the base. This is the emitter. This is the base. This is the collector. This is N doped, is P doped, N doped, and we are asked to find out that at thermal equilibrium, which one of the electronic band diagrams does it have? What is its band diagram? Band diagram. Band diagram on no bias and thermal equilibrium. Thermal equilibrium. These are the two conditions we are given, and we have to find out what's the band diagram. Basically, the band diagram for an NPN, no bias, should look like this. Let's consider the upper conduction band first. The conduction band of an N EC side is lower, is always lower than the P side. So this N side is lower than the P side, followed by again N side, which is again lower. Since there is no bias, the Fermi level in all three cases are at the same level, and the balance band follows pretty much the same behavior. The balance band of N is lower, the balance band is lower for N, higher for P, and this is what the band structure looks like at no bias, zero bias, thermal equilibrium condition. And that relates to our condition B. So the band structure in B corresponds to this, exactly this kind of band structure, and therefore this particular band structure corresponds to the band structure of an NPN transistor at the conditions where there is no bias applied on any of the side, at any side, and everything is in thermal equilibrium. And from that, you should be able to draw the band structures of PNP transistors as well. And if you apply bias, then depending on the bias, the Fermi level actually starts shifting. The Fermi level will not be at the same level anymore. The Fermi level at B for P doped, for N and the two N dopes, they now start varying. So, but since they don't ask for any kind of bias and any kind of non-equilibrium situations, which can happen if you bias it, then we don't have to worry about that here. We just have to worry about the unbiased electronic band diagram configuration. And this is the unbiased electronic band diagram configuration. So that concludes our problem number 29. And we can now move on to problem number 30.